Common drain amplifiers. So this amplifier is another one that gets used quite a lot in integrated circuits because it's effectively the transistor version of a buffer amplifier. So we are going to have a situation that looks something like this, where the drain of our transistor is tied directly to our power supply voltage, VDD. Here is our source node. In a discrete amplifier, we would have our DC biasing circuit just like we had for our last amplifier. So just a simple voltage divider, R1 and R2. Capacitive coupling of our input signal. I think I called this, did I call it CG last time or CN?
CG.
Well, then let's go with CG. We have some signal resistance, R sig, our input voltage. And then over here on this side, let's consider that we're biasing it with a current source carrying some current IS. And we will capacitively couple our load. Here's RL, here's, let's call this CS. And then this terminal is where we take okay. So this is our common drain amplifier. We will talk in a moment about the case when our current source has a associated resistance. So effectively replacing our ideal current source with a practical current source, because that's what a MOSFET current source is a practical current source. But for now, let's look at it. Okay. So our large signal model is going to look something like this, where we're doing nothing but turning all of our capacitors into open circuits and shorting out our input voltage source. So here we have our supply voltage VDD, transistor. Here is R1. Here is R2. Open circuit from our gate capacitor. Signal resistance. Current source IS. Here's our load resistance RL. So it should be pretty obvious that R sig and RL aren't going to influence the DC characteristics of this circuit. All right, so what can we glean from this guy? Well, for starters, we can see that our drain current ID is exactly equal to the current that's being provided by our ideal source here, IS. Why is that important? Anybody have any thoughts? So if we're assuming that this transistor is operating in the saturation region, which we want it to be operating at to make it a good amplifier, what is the drain current equation? I'll do this over here in blue, right? So in saturation region of operation, our drain current, assuming channel length modulation can be neglected, is 1/2 UN C ox W over L VGS minus VTH quantity squared, right? So if our drain current has a fixed value, our drain is effectively being forced to carry a specific amount of current, then what that's doing is effectively establishing what the gate source voltage has to be in order to maintain that, okay? So in some sense, this particular biasing configuration of biasing a transistor with a current source is a way to implement a MOSFET voltage source, because we're forcing a particular voltage to occur at the gate, or a particular gate source voltage to occur in order to accommodate that amount of current being carried by the device. Okay. So if we do a little bit of mathematical manipulation, we could find that the voltage VGS is going to come out to be VTH plus the square root of twice IS over UN Cox W over L, where this bit right here is more commonly referred to as the overdrive voltage. So effectively, this is the voltage that's keeping us in the saturation region, because it's the part that's making, that's in excess of VGS minus VTH just equaling 0 and turning the device on effectively. Okay. So we can say that our gate voltage VG is still just going to be the ratio of VDD multiplied by R2 over R1 plus R2. Our drain voltage VD is obviously just our power supply voltage VDD. And our source voltage, here's where things are a little odd, per se. We have to get mildly creative about how we define what our source voltage is going to be in this case. So our source voltage is going to be the quantity VG minus VGS. So if VGS is VG minus VS, we algebraically manipulate that, we'll find out exactly what our source voltage has to be in order to maintain this device's operation within the saturation region. If we plug in our results here from our algebraic manipulation earlier, we find that our source is going to be effectively at a fixed potential of VG minus our threshold voltage, excuse me, minus 2ID over UN Cox W over L. And we can substitute in our relationship for VG, and this then becomes VDD R2 over R1 plus R2 minus VTH minus the square root twice ID UN Cox W over L. And from here, we know what VG is, we know what VD is, we know what VS is. We have all of the different possible DC biasing voltages that we can need to figure out what our short or small signal parameters and all that kind of stuff are going to be. So what if, so let's put a line here. Oh, I didn't realize I ran out of page, so I guess this is unimportant. What if our current source as a finite resistance. So effectively, what if there is a resistor here in parallel with our ideal current source? What from our analysis is going to change?
That change VS.
So it will definitely change VS. It will actually change our relationship for ID, right? Because our drain current, if I draw it here, so this is the current flowing through the drain to the source. So it's also this current here. But now there are two different paths that our drain current can branch off from, right? So our mathematical analysis of what's going on here, our gate voltage is going to be effectively the exact same thing as it was. VDD times R2 over R1 plus R2, because we haven't added any element on that side of the device, right? Our drain current ID can be written as IS plus our source voltage over our current source resistance. Following through on some math here. And this also has to be equal to 1/2 mu n C ox W over L times the quantity VGS minus VTH squared. From here, I'm going to do this in a different color. This is literally just foiling things out to illustrate something. So VGS minus VTH squared is VGS squared minus twice VGS VTH plus VTH squared. And from that, we could see that VGS quantity squared equal to VG minus VS quantity squared by definition. And no, close. This is going to look like VG squared minus twice VGVS plus VS squared. Give me just a moment, please. Save. I don't want that noise to keep happening. All right, so circling back around here, we have 1/2 mu n C ox W over L times VG minus VS minus VTH quantity squared is equal to IS plus VS over RCS. From here, we have VG minus VS minus VTH squared is equal to 2 over UN C ox W over L multiplied by the quantity, IS plus VS over RCS. This gives us just a second, I'm trying to follow my math here because I see where I'm doing VGS squared. Just a second to follow this here math. All right. I'm just going to write this down and we're going to talk about stuff. We'll figure it out on the fly. So what I have written down here, like I can see on the right-hand side that I've effectively just distributed that fraction thing, which is not a particularly big deal whatsoever. But on the left-hand side, I'm having a little bit of difficulty following my work. The goal here is for us to figure out a mathematical expression that allows us to solve for VS, because VG is well defined because of the voltage divider. VD is well defined because it's literally tied exactly to the power supply voltage. So what I have written down is VG squared minus 2VG VS plus VS squared is equal to stuff that I'll talk about in a moment. The question that I'm asking myself and now aloud to you guys is, what the hell did I do with threshold voltage? And the short answer is, I don't fully know where it went, right? Because to me, when I multiply this thing out, I should be getting a threshold voltage term, right? So what I have right here just represents the VGS squared bit of this guy. I still should have minus 2 VG minus VS times VTH plus VTH squared. Because that's minus 2 VGS times VTH plus VTH squared. And this will equal to, why are you stopping writing, Silas? 2 over, excuse me, 2IS over mu n Cox W over L plus 2 VS over mu n Cox W over L times RCS. Does algebra make sense? All right. So don't have any of this algebra written down on my page, so we're going to have to do it to some extent on the fly. So let's see, I have VG squared minus twice VG VS plus VS squared minus twice VG VTH plus twice VG VS plus VTH squared for my left-hand side of the equal sign. Any algebraic errors there? There is one. Yes. Absolutely right. I just noticed that myself. Thank you. Yeah, so, okay. And that, I think that fixes it, right? Yeah. And then what I'm going to do here is minus twice IS over mu n Cox W over L minus twice VS over mu n Cox W over L times RCS is equal to 0. All right, so rearranging things slightly here, I have a VS squared term. So let's put a check mark by that. Okay. Plus, so let's see. I have a positive 2 VTH that's coming from here. I have a minus 2 VG term coming from here. I have a minus 2 over UN Cox W over L times RCS term that's coming from this guy. And all of this is being multiplied by VS. I think I've got my signs right and I've accounted for all the terms. And then I also have VG squared plus VTH squared. This guy and this guy. And then I have minus 2 VG VTH minus 2 IS over mu n Cox W over L equal to 0. I put it in this form so that we can see it's a quadratic function, where this bit is B, this big thing here is C. So our source voltage VS is going to be negative B plus the square root of B squared minus 4C all over 2. Where a couple of things here. The A term is the coefficient for the VS squared, so that's 1, so that's why I'm not bothering to write it. I'm also making an assumption here, and that assumption is effectively that my source voltage shouldn't be negative in this case. So I'm throwing away the negative solution. The reason why I say that my source voltage shouldn't be negative is because my source voltage should be somewhere between my power supply voltage and 0 based on its literal location in this figure. Like, I don't know how you could drive a non-zero voltage if your supply rails are +5 and 0. Right. So effectively, this figure is drawn from the point of highest potential in the circuit, which is our power supply rail, to the point of our lowest potential in our circuit, which is ground. How we would get a voltage lower than the lowest potential in our circuit doesn't make any damn sense, effectively. So throwing away that negative solution. And we now have some relationship by which we know all of our different DC voltages and all of that kind of good stuff. And we're good to go. Once we know the mathematical value for VG and the mathematical value for VS, then we can back solve for the actual drain current value that's flowing through the transistor itself, which would then in turn allow us to calculate GM, R naught, and all those kind of good things for our small signal model. Okay, so now let's talk small signal. This will be easier. Less mathematical maneuvering. So our small signal or AC model means that we short out our supply voltages, bless you. Here's R1. Here's R2. This open circuit right here that I'm drawing connected to the source represents where the ideal current source was, because to turn off an ideal current source, we replace it with an open circuit. Our coupling capacitor is going to look like a short circuit because we're assuming that we're at a frequency high enough to make that impedance look effectively like zero. Here we have our load resistor RL. Here's where our output voltage is taken. Over here on this side, here's our signal resistance. Oh, and I forgot to draw my input voltage, so let's put that guy in there. Vn as a function of time, right? So this is our starting point for drawing our small signal model. So to me, using the actual small signal model for the transistor, we should have something that looks like this. So there is our input signal. Any signal resistance that our source actually supplies. To save on space, I'm going to observe that R1 and R2 appear as if they're parallel, so I'm going to replace them with a single resistance. And then over here is my gate voltage. This is my voltage VGS. GM VGS in parallel with, that's scrolling on me. R naught. My drain terminal is ground because it was a DC voltage. And then here's the load resistance RL that I'm trying to drive. And this guy right here is our output voltage. Okay. As per usual, our transconductance GM is given by twice UN Cox W over L times our drain current ID that we calculated from our DC biasing point. And our transistor resistance R naught, our channel length modulation resistance, is 1 over lambda ID. So now we'll get into our analysis here. So we can see by inspection that the voltage VGS is simply equal to the voltage present at our gate node minus the voltage present at our output node. VG, in turn, is defined from a simple voltage divider relationship. So that's going to look like our input voltage multiplied by R1 in parallel with R2 over R sig plus R1 in parallel with R2, which should be approximately Vn if R1 in parallel with R2 or much greater than R sig. So just like we had last time, if we want to make sure that we're actually amplifying our input signal, we need those biasing resistors to be much larger than our signal resistance in order to make that happen. Okay. All right, so if we apply Kirchhoff's current law at our output node, so effectively we're saying this current plus this current plus this current is equal to 0. We would have V out over RL plus V out over R naught minus GM times VGS, where VGS is VG minus V out is equal to 0. And we can rearrange this slightly. So we have V out over, or excuse me, multiplied by a factor of 1 over RL plus 1 over R naught plus GM is equal to GM times VG which is the same as Vn times GM R1 in parallel with R2 over R sig plus R1 in parallel with R2. All right, so what does this term I put in the orange curly brace represent? I don't mean that like some symbolic thing, like literally what is it? Yeah. So it's a series combination of conductances, which is the same as a parallel combination of resistances. So effectively, I went slightly too far here. If we had the -1 power there, that would just be literally the exact same thing as RL in parallel with R naught in parallel with 1 over GM, right? Well, when we divide both sides by that, it's like multiplying by that resistance. Parallel. So from here, we can say that our voltage gain is defined as V out over V in is going to be GM R1 in parallel with R2 over R sig plus R1 in parallel with R2. This fraction over 1 over RL plus 1 over R naught plus GM, which is going to look like GM times R1 in parallel with R2 over R sig plus R1 in parallel with R2 multiplied by RL in parallel with R naught in parallel 1 over GM. So, if R1 in parallel with R2 is greater than R sig, that first bit just looks like GM. Well, what about the second part? So we haven't done any numerical examples in this class as of yet, but traditionally, the 1 over GM term is going to be significantly smaller as a resistance value than the channel length modulation resistance R naught will be. And if we're trying to drive a load RL that is larger in resistance than 1 over GM, then we effectively wind up with GM times 1 over GM, or a gain of 1, which is why this is used as a buffer amplifier. We effectively get a gain of 1, but we have the benefit of having near infinite input impedance and all that kind of stuff because of the open circuit and all that kind of jazz. Let's talk briefly, incredibly briefly, what would happen if we were including a current source resistance here. So the current source resistance,
Open circuit, it'd be a path to ground. Gonna be a parallel with RL.
exactly right. So if our current source had some finite impedance, it would literally show up in parallel with RL, which means we don't actually have to do a whole hell of a lot of work to figure out how this thing is going to behave as an integrated circuit. We would just replace that current source with an NMOS transistor that has some characteristic resistance, R naught, sub whatever number we assign to that transistor, place it in parallel with RL, and all of our work is effectively done. All right. Common gate amplifiers, and then we are done for the day. So the common gate amplifier configuration is going to look something like this. This will be a source capacitance. In like so. All right. So looking at this thing from our large signal model perspective, doesn't look as good as I would like. We would have something like this. It's effectively just the standard 4 resistor bias network for a MOSFET device. Right. Where this is our drain current ID. Just for the sake of argument, this is VS, VG, and this voltage right here is VD. We can see very easily VG is just VDD R2 over R1 plus R2. VD is going to be VDD minus RD times ID, and VS is just going to be ID times RS. Um, ba, 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 ba. ID is 1/2 UN Cox W over L. VGS minus VTH quantity squared. And then we effectively have a system of equations that we need to solve, with the understanding, obviously, that VG minus VS is VGS. Summarizing that system solving process, what we get, and I derived this, I think, fully back in 335, is we'd have 1/2 mu n Cox W over L times R. I have a problem here. Let's call this R sig so that there's not two different RSs that are making my brain hurt. RS times VGS squared plus 1 minus mu n Cox W over L VTH times RS times VGS minus 1/2 mu n Cox W over L VTH squared RS minus VDD times R2 over R1 plus R2 is equal to 0, where this thing right here is coefficient A, this thing right here is coefficient B, and this thing right here is coefficient C. And once again, using the good old quadratic equation, VGS in this case is going to be negative B plus the square root of, B squared minus 4AC all over 2A, where we have to throw away the negative solution of this quadratic solve, because it's actually going to give us a device that's operating in the triode region. So it doesn't satisfy the system that we're trying to solve, where we're assuming that we're forcing this to operate in the saturation region. Okay. So if you don't have a system solver, I've given you a means by which to do a quick calculation to figure out what VGS is. Once you know that, plug it in and you know ID. And all of that was derived way back in 335. So now let's take a look at our small signal model. Let's jump straight ahead to the actual small signal model just because we are low-ish on time. So between the gate and ground, we're going to have R1 in parallel with R2. So that should be fairly obvious. We have R1 in parallel with R2 up here, or excuse me, with VDD acting as a short to ground now because we've turned off our power supply voltage. R1 and R2 appear as if they are in parallel, and they are connected directly to the gate terminal of the device. Okay, over here, we have our source terminal. So this is VGS. Here's our source. Between our source and ground, we have the resistance RS. Here we have R sig in series with VN. Here we have our dependent current source GM VGS in parallel with R naught, like so. And then between our drain and ground, we have our drain resistance RD. Here's where our output voltage is taken. Okay. So a couple of things that we hopefully can notice right from the jump here is that this voltage is negative VGS effectively. The voltage that's present at our source is a negative VGS. So I'm saying that because the negative polarity terminal of VGS as we define it for the transistor is at the source terminal. And the positive polarity terminal of the voltage VGS is connected to the gate terminal, which only has those two parallel resistors. So there's no effectively excitation voltage there. So that path just looks like a short circuit to ground. So what this allows us to do is recognize that this current right here is simply V out over RD. The current flowing through our resistor R naught is V out plus VGS over R out. And the current flowing down through our signal resistor there is negative VGS minus VN over R sig. If we apply Kirchhoff's current law. Oh, and I guess while I'm at it, since we're labeling all these currents, let's do this one too. This is going to be negative VGS over RS. Sorry, Stephen, I'm not trying to make you pick up 4 different pens, different colored pens in one hand.
That's what it is.
Yeah. So if we apply KCL at our drain node, we are just going to have V out over RD plus V out plus VGS over R naught plus GM VGS is equal to 0. Okay. With a little bit of algebraic manipulation, this looks like V out over RD plus V out over R naught is equal to negative VGS over R naught plus GM VGS. And from here, we have V out multiplied by 1 over RD plus 1 over R naught is equal to negative VGS times GM plus 1 over R naught. And from here, we can see that VGS is negative V out times 1 over RD plus 1 over R naught over GM plus 1 over R naught. Looks like I went one slight algebraic step further, and I'm calling this negative V out times 1 plus R naught over RD over 1 plus GM R naught. We apply KCL at our source. We have negative VGS over RS plus negative VGS minus VN over R sig minus GM VGS minus V out plus VGS over R naught is equal to 0. And then doing a little bit of algebra, we get negative VGS over RS minus VGS over R sig minus GM VGS minus VGS over R naught minus V out over R naught is equal to Vn over R sig factoring out VGS, we get negative VGS times 1 over RS plus 1 over R sig plus 1 over R naught plus GM minus V out over R not. Yeah, sorry. Is equal to Vn over R sig. And if we substitute in VGS in terms of V naught, or excuse me, V out, what we wind up getting is V out multiplied by 1 plus R naught over RD divided by 1 plus GM R naught over RS plus 1 over R sig plus 1 over R naught plus GM. Minus 1 over R naught is equal to Vn over Rn. Here we get a voltage gain. Let me erase this. I'm going to need more space. R sig times 1 plus R out over R, excuse me, R naught over RD. Over 1 plus GM R naught. One over RS plus 1 over RN, no, R sig. Sorry, I'm using two different notations and trying to keep track of it in my head. Plus 1 over R naught plus GM minus 1 over R naught. Close, and close. And feel free to throw this in your math CAD with numbers if you want. This is approximately GMRD times RS in parallel with 1 over GM times R sig plus RS in parallel with 1 over GM when R naught is large in comparison to the other resistors.